Hello, my name is Stephanie Wyrick, and I'm the General Chair of ICFP 2020. And I'd like to welcome you to Session 4 of ICFP. Our first talk comes from one of my favorite categories of ICFP papers, functional pearls. The emphasis of papers in this category is on the clarity of exposition, and I'm sure that you will agree that this paper is a beautiful read. This paper will be presented by Lionel Parreaux, and he will tell us about the simple essence of algebraic subtyping, principal type inference with subtyping made easy.
Hi, I'm Lionel Parreaux, and I will present my functional pearl on the simple essence of algebraic subtyping. But first, what exactly do we mean by subtyping? Subtyping is a type system feature used to model the relative specificity of types. For instance, the type nat of natural numbers is strictly more specific than int because all nat values are also int values, but the converse is not true. In this work, we focus on inclusive subtyping, in which the types in a subtyping relationship share compatible runtime representations, meaning that no runtime coercions are needed. Inclusive subtyping is useful because it can express relationships between data types based on their variance. For instance, since the list data type is covariant, natlist is a subtype of intlist, so that a list of natural numbers can be used in place where a list of integers is expected. Moreover, we focus on implicit subtyping, which means that expressions of a certain type do not need to be annotated in order to be used at a less specific type. So when we write 1 plus 2, we don't need to explicitly annotate 1 as being of type int, although it's also of type nat. Now let us see a few examples of subtyping. Singleton types are types which represent single values. For instance, the type written 0 is the singleton type of the value 0. Union types are used to type expressions which can be of either one of two given types, and intersection types are used to type expressions which are of both given types. As an example subtyping relationship between these, the type 0 is a subtype of the union of 0 and 1, which is itself a subtype of nat. In fact, subtyping naturally lets us design types which are as close as desired to corresponding operations on values. For instance, we can define the singleton type of empty lists as well as the type of prepending a value to a list. This allows us to use the same list syntax and representation to express things like tuple types, non-empty lists, and everything in between. Subtyping is not just for object-oriented programming. In fact, it has found a host of applications in functional programming. It can, for example, be used for predicate refinement types, first-class modules, XML transformations, and much more. Now, some may be under the impression that functional languages usually try to avoid subtyping, but in fact, subtyping is present in many of those languages, including OCaml, Haskell, and Rust. In Rust, subtyping is used to relate allocation lifetimes. In OCaml, where subtyping is explicit, it is used in many places, such as polymorphic variants, first-class modules, and the object system. In Haskell, subtyping is used in the context of first-class polymorphism to check invert types against signatures. Yet all these languages use type inference engines based on unification, which does not handle subtyping well and limits its applicability. What we'd really like is a way of integrating subtyping in ML-style type inference more consistently and reliably. So first, let's review the way ML languages have traditionally inferred types based on unification. The Hindley-Milner type inference algorithm relies on introducing type variables when the types of expressions are not yet known, and type variables are later unified with concrete types or with other type variables based on the way these expressions are used. As an example, consider the following term, which takes two parameters, x and y, compares them, and returns the smaller of the two. We start from a context gamma, including only the comparison operation, defined to operate on integer values. First, we consider the outer lambda binding x. We assign x the type variable alpha and place it in the context. Then we look at the inner lambda binding y and similarly extend the context with a new type variable beta. Then we consider the if-then-else expression, in particular the condition. Variable x has type alpha and is used on the left-hand side of the less than operation, so we unify alpha with int. Variable y has type beta and it's used on the right-hand side of the comparison operation, so we unify beta with int. Then we consider the branches of the if statement. The first branch has type alpha. The second branch has type beta. And since the if then else must return a single type, we unify alpha and beta, which is the same as unifying int with int and is trivial. The result type of the if then else is alpha. So the result type is int because we have unified int with alpha. The result type of the inner lambda is beta to int, which is int to int. And the final result type is alpha to int, which is int to int to int. Now let's review how to adapt this algorithm to subtyping. Instead of tracking equalities between types, we now track inequalities between types. We do not unify type variables, but instead we keep track of their assumed subtypes and supertypes. That is, we keep track of their bounds. We base our approach on a previous algorithm called MLSub, which was the first to infer most specific types in the presence of subtyping, but whose presentation was complex and difficult to understand. In the paper, the new simple subalgorithm is introduced, which is closer to the traditional type inference algorithm we have just seen and is easier to specify and implement. Going back to our example, we look at the outer lambda again. We extend the context with a new type variable, as before. Same for the second lambda abstraction. We extend the context with a new type variable beta. Then we look at the condition again. The variable x has type alpha, but this time, instead of unifying alpha with int, we simply specify that alpha should be a subtype of int. So we register int as one of the upper bounds of alpha. We do the same for beta. And then we look at the branches. The first branch has type alpha, second branch has type beta, but this time we introduce a new type variable to represent the union of the two branches. We constrain this type variable to be a supertype of the types of both branches, alpha and beta. The resulting type of the inner lambda is beta to gamma, and the final resulting type is alpha to beta to gamma, together with the inferred constraints. So we have inferred the type alpha to beta to gamma, where alpha is less than int, beta is less than int, and alpha union beta is less than gamma, which means that gamma is a supertype of both alpha and beta. Now the call f of 0 and 1 is more precisely typed as nat instead of int. But is this really a type we want to show users? It looks much more confusing than the type we had before we introduced subtyping into the mix. In fact, we can inline, so to say, the bounds of each type variable into the result type to yield a simpler type. This is called bounds coalescing. We replace each type variable occurrence with a composition of the variable's bounds. For occurrences in output position or in positive position, we use a union of the type variable with its lower bounds. Conversely, for occurrences in input or negative positions, we use an intersection of the type variable with its upper bound. We can actually simplify this type further by removing gamma, which is useless, and merging alpha and beta, yielding a type expression which is much more compact and easy to read. Both of these simplifications leave us with a type that is equivalent to the original unsimplified type, despite not featuring the same number of type variables. To understand why that is correct, let us first consider the first simplification. The main insight here is that type intersections can act like upper bounds to type variables, as long as they are added to all the negative occurrences of that variable. Indeed, using the resulting function, in our case, requires an argument whose type is a subtype of the said intersection, which is to say that it must be a subtype of the type variable and of each of its intersected bounds. In our case, the bound is just int. In particular, while users of the function are free to instantiate alpha to whatever type they like, the function will not be callable if alpha is taken to be a type whose intersection with int contains no values. Next, let us look at the second simplification. Here, the insight is that alpha and beta are indistinguishable from each other, since they always occur together in positive positions, which is to say, here, in the result type of the function. Formally, the subsumption relation between two polymorphic types can be used to reason about the equivalence of simplified and unsimplified types. To show that one type subsumes another, that is, tau0 less than for all tau1, it is sufficient to pick an assignment of tau0's type variables which satisfies tau0 less than tau1. For the first subsumption direction, which is to show that the original type subsumes the simplified type, we can pick the following variable assignments. Alpha is left as alpha and beta is taken to be alpha. This makes both types identical, which trivially means that the former subsumes the latter. For the other subsumption direction, we pick alpha to be the union of alpha and beta. Indeed, this instantiation is sufficient to show that the simplified type is a subtype of the original type. Let us once again go back to the type inference example, but this time consider the same term applied to the value 0. We go back to the state of type inference as we left it, and now consider the application of argument 0 of type nat. This generates a constraint that nat should be a subtype of alpha, which is the argument type of the function. So we register nat as a lower bound of alpha. But we are not done yet. We also have to propagate the constraint and check that nat is also a subtype of int, which works out. This gives us the result type beta to gamma with these new constraints, which yields the following simplified type: alpha intersection int to alpha union nat. But what happens if we have a type error? For example, if we try to apply the function with the Boolean literal false. In this case, we use bool as a lower bound of alpha, but while propagating the constraint, we are left constraining bool to be a subtype of int, which obviously leads to an error. As you can imagine, there's a lot more to talk about. You can read the paper to learn about let polymorphism, which complicates the picture quite a bit, the handling of recursive constraints, different approaches to type simplification, the soundness and completeness of type inference, and how subtyping enables typing terms which were not typable before. Finally, I'd like to correct some common misunderstandings about algebraic subtyping. First, union and intersection types are not truly first class. As we have seen, they simply result from the pretty-printing of compact type representations. In fact, they cannot be used directly by programmers as is done in languages like TypeScript or Scala 3, because in our approach, there are syntactic restrictions on the places where unions and intersections are allowed to occur. Supporting first-class unions and intersections would be difficult while maintaining the principal type property, that is, the ability to always infer a most specific type. Moreover, it would make simplification and other algorithms difficult. So the expressiveness of the language studied in the paper is in fact similar to a structurally typed Java, which includes its f-bounded quantification features. Another aspect of algebraic subtyping which I would like to clarify is its relation with invariance. As a typical example of invariance, consider the ref data type, which is the type of mutable variable references, and which is invariant in its type argument. When constraining one ref type to be a subtype of another, it is sufficient to constrain their type arguments both ways. However, we can no longer coalesce the type arguments of invariant types easily, since coalescing relies on the polarity of types to work. Thankfully, there are several ways to work around the problem. We can simply avoid coalescing types in invariant position, or we could introduce new notation to express ranges of allowed type arguments in invariant position. In conclusion, contrary to what many people believe, complete type inference with subtyping is not actually that hard. As long as we restrict the usage of unions, intersections, accept a little more verbosity around variance, and support recursive types. SimpleSub is available online and is less than 500 lines of code, including parsing, type inference, simplification, and pretty printing. That's it for my presentation. Thanks for watching.
Thank you, Lionel. If you're watching this talk as live as an ICFP participant, please look to see if there is a Q&A session available with the author in your time band now. Our next talk addresses the challenges of reasoning about resource usage at compile time. This talk will be presented by D. Wang and is entitled Liquid Resource Types. It is based on work developed by a team of researchers at the University of California at San Diego and at Carnegie Mellon University. The other authors of this paper include Tristan Knoth, Adam Reynolds, Nadia Polikarpova, and Jan Hoffmann.
Hello, ICFP and future viewers of this video. My name is Dee, a PhD student at Carnegie Mellon University, and today I'm going to present our work on liquid resource types, a technique for automatically verifying the resource consumption of functional programs. This is a joint work with Tristan, Adam, Nadia from the University of San Diego, and Jan from Carnegie Mellon. Resource analysis studies the consumption of various kinds of resources in a program, such as time, memory, power, etc. One classic scenario of resource analysis is to find out the time complexity of algorithms. Resource analysis can also be applied to measure gas usage of smart contracts in blockchains, or detect side-channel vulnerabilities in cryptographic code. In this talk, let's focus on a scenario about the time complexity of sorting algorithms. Consider a situation where we want to compare the performance of quicksort and insertion sort. These algorithms are functionally equivalent, and both of them run in quadratic time in the worst case. However, if we already know the input is nearly sorted, which means that most of the elements are in the correct place, which algorithm will have a better performance? In fact, insertion sort can achieve linear time complexity on nearly sorted data. So instead of a quadratic upper bound, how can we express a fine-grained time complexity of insertion sort? Look at the animation that might help you recall how insertion sort works. It goes through the elements in the list iteratively and tries to move them to correct places via swaps. Indeed, we can have a better estimation than the quadratic worst-case bound. The number of swaps is proportional to the number of out-of-order pairs in the list. Now, here comes a challenge that our work wants to address. How can a resource analysis formally describe and also automatically verify such a complex value-dependent resource bounds? To achieve this, our work follows a line fork on liquid types, which support automatic verification of functional properties. For example, a function returns the absolute value of its input. Reason augments an existing liquid type system with a simple construct. Types can be annotated with potentials. For example, a list where each element carries 1 unit of potential. Potentials can be used to pay for the cost in the program. So if a function consumes all the potential in the list, the cost bound is linear in the length of the list. A major limitation of Reason's type system is that it only supports linear bounds. In our work, we proposed liquid resource types with the ability to express a lot more non-trivial resource bounds. A key idea is that the potentials can be inductively specified from the formation of data structure themselves, which allows us to express the time complexity of insertion sort. In general, liquid resource types provide a mechanism for expressing and verifying superlinear value-dependent resource bounds. We formalize and prove the type soundness with respect to a cost semantics. We also implement an automatic type checker for liquid resource types and evaluate it on a suite of challenging examples. Now I have talked about motivations for resource analysis and the main contributions of our work. Before diving into the technical details, I want to first introduce 2 important concepts that our system is built upon: liquid types and the potential method. Liquid types can be seen as a refinement type system, where types are annotated with logical predicates that can constrain the values. A refined type can be written as a subset. B is the base type of the value, and psi is the logical predicate. For example, natural numbers can be defined as a refined type with integers. The predicate can mention a special variable v, which reflects the value of the inhabitant. In addition, arrow types can be dependent, and the result type can be annotated with a predicate that references the argument. For example, the type showed on the slide specifies a function that returns a list whose length is 1 plus the length of the input list. The potential method for amortized analysis is a classic approach for algorithm analysis, which can be dated back to 1985. The high-level idea is to treat a program execution as a transition graph among program states, and each arc on the graph contains the actual transition cost between 2 states. To analyze the resource consumption, we devise a potential function phi that maps each program state to a non-negative number, such that the potential of the state is enough to pay for the actual cost of the current transition and the potential of the next state. In this way, the potential of the initial state provides an upper bound on the actual resource consumption. Our prior work, Reason, has combined liquid types with the potential method to automatically verify resource bounds of functional programs. The idea is to annotate types with potentials. The potential annotation and the logical predicates are in the same refinement language. The difference is that potential are numeric, but predicates are Boolean. The potential annotation then defines a potential function on the values of the annotated type. For example, the type on the slide describes a natural number carrying potential equal to 5 times of its value. Potential annotations can also be conditional. The type just showed on the slide describes a list of numbers, where each non-negative element carries 1 unit of potential. With this construct, Reason is able to express and verify value-dependent linear resource bounds. Take a look at the functional program on the slide. The insertion function, as a subroutine of insertion sort, inserts an element x to a proper place in the list XS. We use tick expressions, marked in blue, to specify a resource metric. In this program, we use ticks to count the number of recursive calls. Reason can verify a value-dependent linear resource bound shown on the slide. However, it cannot express a type for insertion sort because it can only distribute potential uniformly within a list, but insertion sort requires a mechanism to describe pairs of elements in the list. Okay, now I have introduced the 2 important building blocks of our work, liquid types and the potential method. Now we'll show how our work extends prior work with 2 powerful mechanisms and how to reduce type verification to constraint solving. Our first mechanism is inductive potentials. Rather than only put potential to elements in a data structure, we can specify potentials inductively from the formation of the data structure itself. The code on the slide shows the definition of QList, a variant of list types with quadratic potentials. Here, the Q constructor maintains that the tail of the list carries 1 more unit of potential in each element than the head, and the tail itself is again a QList. How does such a simple, constant potential annotation lead to an overall quadratic potential function? Well, let's do a calculation. Suppose a list L of elements v1, v2 through vn is of type QList T, where the value of type T carries p units of potential. Then, for every element vi in the list, it carries p units of potential, and by the definition of QComs, it also indicates extra potential equal to the number of elements to the right of vi. Therefore, the obtained potential function is quadratic in the length of the list. More interestingly, we can use value-dependent inductive potentials to express fine-grained bounds. The type IS list shown on the slide is almost identical to the type Q list, except that the extra potential required by the ISConst constructor is not a constant 1, but a conditional expression that evaluates to 1 if and only if the element in the tail is less than the head element. In other words, the potential specified by IS list is exactly the number of out-of-order pairs in the list. In this way, we formally express the fine-grained time complexity of insertion sort in our type system. However, inductive potentials on their own are difficult to use. The potential annotations are built into the data type definitions, so any slight change in the analysis or in the resource metric requires redefining a new data type. To address these issues, we have proposed a second mechanism. Abstract potentials. In liquid resource types, we allow data types to be parameterized by a numeric potential extractor. Thus, both QList and ISList can be seen as instantiations of a more general list type. The list type is parameterized by a numerical function Q, which takes 2 list elements as arguments. Then, in the const constructor, we use the function Q to define the amount of extra potential added to the tail. With this abstract type, QList can be defined as list with Q instantiated with a constant 1 function, while ISList can be defined as list with Q instantiated with a conditional expression that compares to elements. Now you may wonder, with this new construct, how can type checking in your type system be automated? Let's use the insertion sort program as an example to illustrate the reduction from type checking to constraint solving. The program uses insert to iteratively place elements to the right place. Our system does not infer types, so we assume that we have the type signature for recursive functions insert and sort. Our type checker goes through the program in a top-down manner and generates constraints on the fly. For the sort function, initially, the context only contains the argument xs. After the pattern match, if xs is an empty list, then it carries 0 potential. But because it is also free to create a new empty list, the nil case is verified. Otherwise, if xs is not empty, then the potential of xs is transferred to the variables head and tail, the components of const constructor. Use the definition of const, we can unfold the type signature and obtain the potential stored in head and in tail. Then in the rest of the program, there are 2 function calls. At this point, we need to split the potential in the context into 2 parts, and each part is used to pay for the cost of 1 function call. In the top-down phase, we don't really know how to split the potential, so we create symbolic potentials annotations and generate constraints among the symbols. Note that for the call to sort, it's wrapped by a tick expression, so we need to use the potential to pay for the tick. For simplicity, let's assume that the type checker uses the potential stored in head to pay for the tick. So in the context for type checking the call to sort, the annotation on head becomes p2 minus 1. Now let's take a look at the constraint generated by our type checker. The constraints assert the existence of p1, p2, q1, q2. First of all, there are constraints specifying the potential split. The potential in different parts should sum up to the original potential in the context. Then, for the tick, we need to ensure that the potential is enough to pay for the cost, which means that the potential after the tick is still non-negative. Finally, the type checker generates constraints for function calls. For the call to sort, we assume that the type parameter A is instantiated with an unknown potential annotation S, which is used to thread some potential to be used by the later call to insert. Similarly, we use the signature of insert to generate a constraint on S. Now, after the type checker generates all the constraints, it tries to solve the constraints by finding proper instances of P1, P2, and Q1, Q2. These constraints are essentially second-order conditional linear arithmetic constraints, and solving such constraints automatically is a well-studied problem. So in this way, we obtain an automatic type checker for the liquid resource types. As for theoretical aspects, we formalize and prove the soundness of liquid resource types with respect to a cost-aware small-step operational semantics. Our soundness theorem ensures that a well-typed closed program will never run out of resources if it starts with an amount of resources equal to the initial potential specified by the types. Details of the theoretical result can be found in our paper and the technical report. After I explain how our type system formally expresses and automatically verifies resource bounds with liquid resource types, you might wonder whether the system is effective in practice or not. Let's first take a look at some reusable resource annotated data types, which we'll use to specify the type signatures for our benchmark programs. The first one for quadratic potential over list we have already shown during the presentation. The second one specifies exponential potential over list by doubling the potential in each element of the tail in the econst constructor. The third one defines binary trees. To capture tree height in the potential, the Knoth constructor adds q more units of potential to the element in the subtree. So basically, an element at the leaf carries q times h units of potential, where h is the depth of the leaf. In this way, we can express a resource bound like O n log n if the binary tree is balanced. The fourth one also defines binary trees, but it assigns potential to a specific root-to-leaf path on the tree. This is achieved by parameterizing the type biological predicate as a guide to a specific leaf. With these data types, we are able to express and verify the time complexity of 12 challenging benchmark programs. As the table shows, the resource bound can be polynomial, non-polynomial, or value-dependent. Our prototype implementation is reasonably efficient, and no other automated resource analysis system can verify all of our benchmarks. Details of the benchmark programs can be found in our paper and the technical report. In summary, we proposed liquid resource types as an extension of liquid types to express and automatically verify value-dependent superlinear resource bounds of functional programs. We formally prove the soundness of our type system and implement a prototype type checker that is shown to be effective in our experiments. Our work still has a bunch of limitations. For example, our system only supports inductively defined potentials, does not allow multivariate bounds like n times n, and we don't have a type inference algorithms yet. These limitations are interesting research directions, and we hope to explore some of them in the future. Thanks for your attention.
Thank you, Dee. At this point, if you're watching this stream live as an ICFP participant, please remember to look to see if there's a Q&A session available in your time band so that you can discuss this work with the author. Our next talk will be presented by Glen Mével, who will be presenting a concurrent separation logic for multicore OCaml.
So welcome to this talk. I'm Glen Mével, and with Jacques-Henri, Jourdan, and François Potier, we've been working on a concurrent separation logic for multicore OCaml. What does that mean? Our aim is to verify fine-grained concurrent programs in the setting of the multicore OCaml memory model, which is a weak memory model. In this talk, I present a concurrent separation logic with a notion of views. So a few words about multicore OCaml. As the name suggests, it is an extension of the OCaml programming language with support for multicore programming. It comes with a weak memory model, which has been formalized in a paper at PLDI 18, and it features two flavors of locations, which are termed atomic and non-atomic. By the way, if you're interested in the garbage collector of multicore OCaml, please have a look at this other ICFP paper whose title is Retrofitting Parallelism onto OCaml. So what is the challenge here? Essentially, the challenge is dealing with the weak memory. Under sequential consistency, traditional concurrent separation logic gives you a points to assertion, x points to v, which expresses your unique ownership of the memory location x, and which also says which value is stored in x. And then you have the usual Horst-style resolving rules, and this assertion gives you ownership of x, but you may want to share this ownership among all threads. And to do so, an usual solution is to put the assertion in an invariant. Intuitively, an invariant holds at all times, and its contents can be accessed equally by all threads. So here, we can put x points to something in an invariant, which we denote by boxing the assertion. Then any thread can access x as long as it preserves the invariant. Now, what breaks under a weak memory model is that each thread now has a different view of memory. This notion of view is crucial because it means that some assertions, like the points to assertion, are only valid with respect to the current view of a thread. We call these kinds of assertions subjective assertions. But on the other hand, invariants hold equally for all threads, so they can only contain objective assertions, where by objective we mean non-subjective. Then, the challenge is to keep a program logic which feels simple and natural enough, but at the same time is able to deal with subjectivity and allows subjective assertions to be shared between threads. I just spoke about the view of a thread and how it is central to the challenge of weak memory, but I haven't defined this concept yet, so let me do that now. Because of weak memory, each thread only knows a subset of all writes that have happened to the shared memory. This affects how the thread reads and writes the memory. For example, once it has learned about a write, it cannot read from earlier writes anymore. This is an example of what a weak memory model would say you. And this subset of write events, we will call it a view. So the view of a thread, is the set of the write events it knows about. Now we want to manipulate these views from the logic. And for that, we add new kinds of assertions. The first new kind of assertions is this upper row u, where u is a view. We pronounce it as we have seen you, and it means that the current thread knows all writes in u, so it is an assertion about the current view of the thread. And the second new assertion is p at u, where p is an assertion and u is a view. It means that p holds in the eyes of any thread which has seen u. For example, let's say that P relies on knowing a given write event, then it requires the current view to contain that write event, so certain P is subjective. But instead, we can assert that whatever the current view is, if it contains that write event, then P holds. And by saying this, we do not depend anymore on the current view, so saying this is objective, even though P may be subjective. And that's what P at U means when U contains the given write event. So we can make a subjective assertion objective by specifying the view at which we see it. And why is it interesting? Because these new assertions are complementary. More precisely, in our logic, an assertion P is equivalent to an objective assertion. Any assertion P is equivalent to an objective assertion of the form P at U, and an assertion of the form upper row U for some view U. This shows in particular that view assertions of the form upper row U capture all the subjectivity of the wake memory, and this decomposition will allow us to share subjective assertions between threads by using a different mechanism for each part. The first part, P at U, is objective, so it can be shared via an invariant, just as in usual concurrent separation logics. Regarding the second part, sharing upper U means exchanging information about write events between threads. So in other words, it means synchronizing. So we will rely on some form of thread synchronization that is provided by the memory model. That was the main idea of this talk. Now I show you what is in our program logic to reason about programs in memory, and I'll start with the simplest thing, which are atomic locations. For atomic locations, we have unusual looking points to assertion. Atomic X points to V, which means that we own the atomic location X, and X stores the value V. We are able to say such a thing because atomic locations in Multicore OCaml behave in a sequentially consistent way. At any given time, all threads see the same value for X. In particular, this assertion is objective. Then it should come as no surprise that atomic accesses obey the usual or triples, both reads and writes. Where things become interesting is for non-atomic locations. The non-atomic locations of Multicore OCaml have a relaxed behavior. In the logic, we still have an assertion X points to V, but its meaning differs slightly. It still asserts the unknown shape of X, but instead of saying that the value of X is V, it says that we have seen the lattice write to X, and this write bears the value V. And this is the typical subjective assertion. There is no such thing as the global value of X because different threads do not necessarily know about the same writes to X. What is really nice with this points to assertion is that it also obeys the standard rules. So we have a simple looking assertion that behaves in a natural way. The price for it is that the assertion hides more behind the skins and it is subjective. So we cannot share it only by using an invariant. So let's see how we can share it nonetheless, and for that, let's consider the typical code pattern, which is called a spin lock. Let's say we have several threads that want to access the same resource, such as a single non-atomic location. Then we can use an atomic flag to guard that resource. When the flag is true, the resource is taken, and if you want to acquire it, you need to wait for it to become available. Now, from a logical point of view, the lock can be seen as guarding an assertion P, which may be subjective. For example, it may be a non-atomic points to assertion, as we have seen just before. The first thread has P before releasing the lock. The second thread will get P after it has acquired the lock. So we want P to be transferred from the first thread to the second one. To see how that works, let's consider only the concurrent set operation that succeeds, because that's that's when the transfer happens. As we've seen, we decompose P into an objective part and a subjective part so that we can transfer each part. The first part, P at U, is objective, so it can be transferred using an invariant as usual, so we get rid of it. So now we are down to the problem of transferring a view assertion. As I said before, we need some form of synchronization on here. What Multicore OCaml gives us is a happens before relationship from the release write to the acquire read. So instead of adding new primitive to the language, Multicore OCaml made the choice of performing release acquire synchronization on atomic accesses. And we need to reflect this in our program logic, and we do so by extending the atomic points to predicates. So recall that atomic points to V means that X stores the value V. We now extend this assertion so that atomic locations stores the pair of a value in the view. So accesses still behave the same with respect to the value, but they also perform a release acquire synchronization on the view. So when writing, we push into the shared location any information we have in the local view, so that's a release write. And conversely, when reading, we pull into a local view any information stored in the shared location. So that's an acquire read. And with this in mind, let's come back to our spin lock. As we have seen before, the spin lock has two operations, release and acquire. In the interface, it works in assertion P. We give the spin lock a specification, which holds under some invariant. And now, to prove this specification in the usual separation logic, with sequential consistency, we state an invariant like this. We are either locked or unlocked, and in the latter case, the invariant itself holds the assertion P. Now, in our program logic with weak memory, P may be subjective, but everything in the invariant has to be objective. So the invariant we state instead is that one. In fact, it is the same as in usual separation logic, but we add views. To remain objective, we make it explicit at which view we have P, and we say that it is the same view as is stored in LK. In other words, P holds in the eyes of whoever last released the lock. So the P at U in the invariant obviously allows to transfer the objective part of P, while the atomic location itself allows to transfer the subjective part of P. So that was the proof of the spin lock. And in addition to this example, we did more case studies with different kinds of locks, algorithms for mutual exclusion. And in all of these examples, we have been experiencing the same pattern of sprinkling views over our invariants. So a general method for proving the correctness of a concurrent data structure is to start by reasoning as if we had a sequentially consistent model, express the invariant in the usual concurrent separation logic, then identify where synchronization happens and make it explicit by adding views. To sum up, I have presented a program logic for Multicore OCaml based on isolating subjectivity into views. I argue that this logic enables concise and natural reasoning about how threads synchronize. There is more in the paper, namely how the logic is realized by building on top of a lower level logic, and we also have more case studies. This entire work is mechanized in the Coq proof assistant using the Iris separation logic framework. So we have a verified proof of soundness on the tile language with which we can write programs and prove them correct under using our program logic. And in the future, we would like to verify even more data structures, and also we would like to investigate data races. Because data races are currently not supported by your logic, even though the underlying memory model gives a few guarantees about them. Thank you for your attention, and if you have seen our previous slides, you hold the right to ask questions now.
Thank you, Glen. If you are watching this talk live as an ICFP participant, please look to see if there is a Q&A session available so that you may discuss this work with the authors of this paper. The fourth talk of this session is entitled Composing and Decomposing Op-based CRDTs with Semidirect Products. This paper has been written by Matthew Wiedner, Christopher Meekjohn, Heather Miller, all from Carnegie Mellon University. Matthew will be presenting the talk.
Hello, I'm Matthew, and I'm going to be talking about our paper, Composing and Decomposing Op-based CRDTs with Semidirect Products. And this is work with Heather Miller and Christopher Meekjohn. So to start off, let's say you're building a web app where you have some kind of stored state that can be shared between different users. So this is basically any website nowadays, but some specific examples I have in mind are things like Slack or Facebook groups, or maybe a conference management website. So the usual way you'd build this is you have a server, and when a client wants to change their state, they send a message to the server responds, and then the client updates their own view of the state. Okay? But we know that actually the server is probably not a single machine, but a bunch of machines working together in the cloud using message passing. Now, a lot of work has gone into making these systems efficient and easier to use, but it still can get pretty complicated. It's easy to introduce subtle bugs, and you need a lot of specialized knowledge to write the server-side code. So CRDTs provide an alternative way to build applications that use shared state. The CRDT stands for conflict-free replicated data types. And basically, they're like ordinary data types, except that they're shared between a group of users and they intelligently sync up with each other in the background. So as an example of how you might use this, on the client side, you can use this snippet from the Legion CRDT library. So the first two lines here set up the group state basically and connect to each other. And then after that, if you want to have a shared set, like maybe a shopping list, all you do is instead of making an ordinary set, you make a Legion set. And then you can just use this like an ordinary data type. So for instance, you can say shopping.addMilk to add milk to the set. And what this will do under the hood is it updates the local state immediately, and it also lazily broadcasts the operation to other users and replicas, who will then apply the operation to their own copy of the state. And CRDTs are neat because they're a programming language's way of solving a systems problem of how to build these applications with shared state. And in particular, the way you design them is principled and mathematical. So at least in theory, it should be harder to introduce bugs when you use them. So some pros, you have this simple client-side programming model, like I described, where you basically just switch out your ordinary data types with CRDTs, and then they run on top of a generic server. They have minimal latency, they work offline, can support end-to-end encryption. Some cons is that they're targeted at data that's shared in small groups only, basically because everyone has to share the state with each other and sync up, so you don't want the group to be too big. Also, they have automatic conflict resolution, but this algorithm will make some specific choices which won't be appropriate for every app. They're not for data that needs locking, but the biggest thing that I want to talk about is the fact that you have to design the conflict resolution algorithm for each data type, which is a difficult and ad hoc process. So in practice, what this means is that you're restricted to using a few common data types with restricted interfaces, basically whatever CRDT researchers have figured out within the past 10 years. In this work, we present a compositional design technique for op-based CRDTs, which we call the Semidirect product, which is supposed to address the difficulty of designing CRDTs. What it lets you do is you take two input CRDTs, here C1 and C2, you take, and they have to operate on the same state type. You take a bit of extra information in the form of this function that we call the action, and then what you get out is this CRDT that supports the operations of both of their input CRDTs and also resolves conflicts between them in a natural way. You can use this for composition of CRDTs directly, which is where you take two existing CRDTs and combine them to get a CRDT with both of their operations. In practice, usually you can use this to add operations to an existing CRDT. So for instance, we show how to take an integer counter CRDT and add multiplication operations, or take a list CRDT, add a reverse operation, or take a dictionary CRDT that maps keys to values, and add a functional mapping operation, which applies some operation to every value in the dictionary. We can also use our semidirect product for decomposition, by which I mean taking an existing CRDT design and exhibiting it as a semidirect product of two simpler CRDTs, often commutative data types, which are sort of the simplest type of CRDT. So for instance, if you have a set CRDT, we show how to decompose it into two simpler commutative data types, one that only has add operations and one that only has removes. And likewise, with some generic resettable CRDT designs, we decompose them into the non-resettable and the resettable parts. So to explain our construction, I first want to give a bit more background on how CRDTs work. So we call our system model, when one user updates the state, they update their local state immediately, and also broadcast the operation to other users in the background. So the problem can come if you have conflicting operations. For instance, let's say Alice and Bob share an integer, and Alice sets the value to 3, while at the same time Bob sets the value to 5. So then later they'll sync up with each other and they see that they have a conflict. So they have to decide what to do in order to get the same answer. So one main conflict resolution technique that's used in CRDT designs is to make operations commute. So for instance, in the Alice and Bob example, let's say that they're actually counting something, like the number of clicks on an ad. In that case, when Alice sets the value to 3, what she actually wants to do is add 3 to the current value. Likewise, when Bob sets the value to 5, he actually wants to add 5. But these addition operations commute. They'll both get the answer 8 once they exchange operations. So that's fine, we've avoided the conflict. You can also use commutativity to design clever sequence types that don't have conflicts. Another thing you can do is to reason about causality. So I'll go into more detail about what I mean by causality on the next slide. But a simple example is if Alice and Bob share a shopping list. Say Alice adds milk to the shopping list. Later, Bob sees this operation, but he's already bought milk at the store, so he's going to remove milk from the shopping list. Then what a CRDT will do is it'll send out a message to the other users saying, remove milk from the shopping list, but only after applying Alice's operation. So we notice that anyone else will apply add and then milk in that order, so they'll end up in the state where they don't have milk on the shopping list. And thus everyone will end up in the same state. There's no conflict anymore. So in general, when I say reasoning about causality, I mean reasoning about the causal order on operations. This is the partial order defined according to 3 rules, which I'll illustrate using this diagram. So here time goes to the right, and diagonal arrows indicate message sending. Okay, so the first rule is that if some user, like Alice, sends 2 operations in a row, then the first operation is less than the second one under the causal order. For instance, here adding milk is less than adding bread. The second rule is that if, say, Alice sends a message, Bob receives it, indicated by the first diagonal orange arrow, and then Bob sends his own operation, like remove milk here, then the first one is less than the second one. So here add milk is less than remove milk in the causal order. And the third rule is transitivity. So by what I just said, add milk is less than remove milk, and by the first rule again, remove milk is less than add eggs. So then we dictate that also add milk is less than add eggs by transitivity. Okay? So note that this is a partial order. It's possible to have a situation like this, where these 2 add milk operations are neither less than nor greater than each other. In this case, we say that they're concurrent. Then the good thing about causality is that CRDTs can query the causal order. Basically, you can attach metadata to operations when you send them over the network, so everyone agrees on what the causal order is. And then this lets you make definitions, like for a set CRDT, you can say X is in the set if there is an add X operation that is not less than any remove X operation. Okay? Because this rule explicitly reasons about causality, there's no possibility of conflict. Even if people get operations in different orders, they'll come to the same result. And you can see in the example I have here, milk is going to stay on the shopping list according to this rule, because Charlie's add milk operation is not causally less than any remove milk operation. Okay. So again, here are the conflict resolution techniques for building CRDTs, commutativity, and reasoning about causality. What our semidirect product does is it provides a uniform and reasonable way of reasoning about causality so that CRDT designers don't have to do it from scratch each time. This is good both for coming up with rules, like this rule that I've specified here for a set, and it's also good for implementing them. So if you just look at this definition, it's not entirely clear how you would implement this efficiently without just looping over the full history of operations every time you get a new one. Okay? So what our semidirect product enables is a new CRDT design workflow. So starting from an ordinary data type that you want to turn into a CRDT, you first design commutative data types for simple subsets of operations, and then you glue together those subsets with semidirect products, and it'll handle conflicts between the operations that don't commute in a natural way. In our experience, this design workflow works for most existing CRDT types, plus novel ones. Okay, now for the rest of the talk, I want to give an example of how our semidirect product works. In particular, a simple example, we're going to start with two commutative data types, an integer register that has add operations and an integer register that has multiplication operations. And we want to compose them into an integer register that supports both kinds of operations at once. Okay, so an example of something you can do with this data type is you start in state 1, multiply by 3, and add 1. But of course, the tricky part is that multiple users might be making these operations concurrently, and we have to resolve conflict between them. So add operations alone are easy. They already commute, so there's no conflicts. Similarly for multiplication operations, but they conflict with each other. For instance, if Dave and Mary are sharing a counter, and then Dave says to multiply his state by 3, while concurrently, so without coordination, Mary says to add 1 to her state. Then after they exchange these messages, if they just apply them literally, they'll end up in different states. Mary's going to be 6, and Dave's going to get 4. So this is a conflict. Okay? So now to resolve this conflict, you're going to make the choice that in the face of a conflict, adds should go before mults. So basically here, Mary is in the right and Dave is in the wrong. We want to get the answer 6. And our observation is that to make this happen, if you're like Dave here and you get the add and the mult in the wrong order, you can fix it up by acting on the addition with the multiplication. Okay? So here what we say is when Dave receives Mary's add 1 message, instead of applying it literally, he's going to act on it with this multiply by 3 message and add 3 instead. So then he gets in the state 6 as well. We've solved the conflict. And this works by the distributive law of multiplication over addition. Okay? So more generally, if we have a more complicated situation like this one, we make the rule that when you receive an add operation, before applying it, you first act on it by all concurrent multiplication operations that you've already received. Okay? So in this example, Dave has multiplied his state by 2 and then added 1, while concurrently, so without coordination, Mary multiplied by 3 and then added 4. Okay? And now they sync up, so they exchange these operations. So Dave gets the multiply by 3 operation from Mary, he'll just apply that literally. But then when he gets this add 4 operation, he first looks in his history and sees that he's already applied a multiply by 2 operation that is concurrent to the add 4. So he's going to use that as a transformation and add 2 times 4 instead to get 17. Likewise, Mary receives the multiply by 2 operation from Dave. She applies it literally. And then when she receives the add 1 operation, she's going to transform it by her mult3 operation because that's the concurrent message that she's already applied. So she adds 3 instead of 1. And then they both end up in state 17. So the fact that they both end up in the same state is again just a consequence of distributivity. Another way of stating this rule is that if you receive an add m message from another user, then you turn it into add of n1 times nk, etc. times m, or mult n1 through mult nk, or all the multiply operations that you've previously received that are concurrent to the one you just received. Okay? And this rule is the same general rule that we use in the full semidirect product construction. Basically, you give some action which says if I receive one operation after a concurrent operation of another one, I'm going to act on it with this action. And this works in general subject to algebraic constraints on the input CRDTs and on the action. Okay, so that's all I wanted to say about our construction. Just a quick recap. CRDTs are a nice programming language's way of building systems that act on shared state, like web apps. The way you use them is that programmers just replace ordinary data types with CRDT versions on the client side, and then the server is just a messaging server. If you want more information about these, I encourage you to check out the website crdt.tech, which has a collection of nice resources. So in our work, we present the semidirect product, which is a compositional design technique for CRDTs. It resolves conflicts between operations by reasoning about causality in a uniform way so that you don't have to. And it enables a new CRDT design workflow where you start with a data type that you want to replicate, you design commutative data types for subsets of operations, and then you glue these together with semidirect products. Okay, and that's all I have to say. So thanks for watching, and I hope there'll be some questions.
Thank you, Matthew. If you are watching this talk live as an ICFP participant, please remember to join the Q&A session if it is available in your time zone. Our next talk is a new approach to impredicative polymorphism in the Glasgow-Haskell compiler. This work has been developed by Alejandro Serrano, Jorian Hogg, Simon Peyton-Jones, and Dimitris Vitiniadis. Alejandro Serrano will be giving the presentation.
Hi, I'm Alejandro. I'm going to talk to you about a bit how we brought impredicativity into GHC. But first of all, what is impredicativity? Take a function like map. It has two type arguments and it takes a function, a list, and returns a list. Because this function is polymorphic, we can use map with a wide range of types. We can use map even and then get a function from list of ints to list of bools, or we can have map of greater than and then we have a list of ints to a list of functions. But if now we want to use map with this function, which takes an argument which itself has a polymorphic type, in many cases we cannot really use this. Polymorphic types, those types having with a for all, are often not first class in many programming languages. Impredicativity is exactly the feature that allows you to instantiate a type variable like a or b in map with a polymorphic type, a type which has a for all in front. SystemF, which is the basis for GHC core, is itself impredicative. You can always instantiate with a for all type. But you have to be very explicit about it. You need to annotate. In fact, in SystemF, you need to annotate every time you instantiate with a type application, like I'm doing here with add for all a to a. And you also have to annotate every time you generalize, every time you need to have a for all in a type with a big lambda, like I'm doing here in the big lambda for the first argument. So the problem actually is not impredicativity, but impredicative inference. We want to write something like here, where we cons an identity function to IDs, which is itself a list of for all a to a's, and we want the inference engine to be able to add anything we need. But there are several questions. First of all, how do we instantiate the cons? Henle-Damas-Milner, for example, which is one of the best known inference algorithms, does not allow polymorphic instantiation at all. The second question is, how do we choose to generalize? How do we know that we have to have a big lambda exactly at the point we need it and not somewhere else? There's been a lot of work about impredicative inference. There are so many related work. Here I want to present Quick Look, which is a new idea in which what we do is we introduce a new quick look phase during instantiation which discovers impredicativity as much as possible, and then the rest of the type checking just remains as it was. Let me show you an example. For example, I have here cons, ID, IDs, where instead of using ID directly, I'm putting this into a local binding, but here you can see all the types. If you do inference with Henle-Damas-Milner, what will happen is that you instantiate the type of cons and sort of you are introducing cons applied to one type variable you don't know. I'm going to call it alpha here, and then you have the argument ID and IDs. The type of the arguments are then alpha and list of alphas. The question now is, what is alpha, of course? And if you have a declarative spec, maybe you guess the instantiation, or if you have a type inference engine, the type inference will do unification and try to figure this out. But the thing is, no instantiation with for all types without for all type works. So this example is rejected by Henle-Damas-Milner. How does it work with Quick Look? Well, you start with the same step, you instantiate the type of cons, and at this point, you have a quick look at the arguments. You try to get as many information about the impredicativity you need by looking and having a peek at the arguments. In this case, we're going to learn nothing from the first argument IDs, And from the second argument, we're going to learn that alpha has to be exactly for all AA to A. At this point, what we know is that the type of these arguments are not just any alpha, they are exactly for all AA to A and listed for all AA to A. And there is nothing else to guess, and type checking can succeed. Now, I've said that we learn nothing from ID, but from IDs, we learn that alpha must be for all AA to A. So you might be wondering why, what's the difference between these two arguments? Let me try to explain this. Here are the types we are pushed, so the types we get from the instantiation, and the types that are obtained from looking at the type of the variables. In the case of ID, the type which is pushed is this single type variable alpha, and the type we get from the variable is for all AA to A, and from IDs it's the same, but everything is wrapped in a list constructor. So actually, in the case of IDs, we have only one possibility. In order for the list of alpha and the list of for all AA to A to be equal, just one has to be, alpha has to be for all AA to A. Now for the second case, we actually have two possibilities. It could be that alpha is for all AA to A, but we have another option. At this point, we could instantiate, so the for all A to A becomes beta to beta, and then we make alpha equal to this beta to beta. The difference here is that alpha in the second case is what we call guarded, which means it appears under a type constructor. And the key idea is that the instantiation relation becomes simple equality when you have a type constructor on top. So in the second case, you have nothing to decide. There is only one choice, so you take it. If you have a single type variable lying around, like in the type of IDs, you don't know what to do, so we just say, well, at this point we learn nothing. And actually it can be the case that quick look guesses no information. Let's, for example, cons ID with an empty list. In this list, we will instantiate the type of cons, have a quick look at the arguments, and we will learn nothing from ID, and we will learn nothing from the empty list. So we need to fall back to monomorphic instantiation, and the result will be that the inferred type is the most usual list of tau to tau, where these taus are monomorphic types. We can also get some other information into account. Imagine, for example, we have this call to single ID. Well, we have a pretty similar story with the arguments. The type of ID is going to be alpha when we push it, and then we have a for all AA to A. So we have two choices here again. We can make alpha equal to for all A to A, or we could instantiate. So quick look gives you no information here. But if we have a better look, we can also take into consideration the type of the result. And in that case, we can play the same trick as we did for the cons of ID with IDs. The type we get pushed is for all AA to A, that's from the annotation, and the type we get from the instantiation is list of alpha. So we can make alpha equal to for all AA to A. So by knowing the expected result type, we can get even more impredicative information. And this will actually inform us to get a bidirectional type system instead of a single directional one as Hindley-Milner is, for example. But the question is when to stop quit looking. Up to now, we've only dealt with variables. So everything was one application, and this application had arguments, but those arguments were all variables. We can actually go deeper and inspect nested applications. And if you think, for example, into this call, cons ID to cons ID IDs, in order for the topmost cons to be correctly instantiated, you need to go up to the IDs so that you learn that, well, this should have a type of list for all AA to A, and this will inform both cons. So you gain something by inspecting nested applications. But we do no more. We really want to keep this simple. We don't want to go into environmental changes, so we don't inspect lambdas, we don't inspect lets, because these introduce new things into the environments. And we don't try to inspect things with multiple branches, like ifs or pattern matching, because this will imply that we need to not only unify things in a simple way, we would also need to consider the cases in which these two branches don't have a similar type. So we just really want to keep it simple, and we found that nested application seems to be a sweet spot. So you really gain a lot of information by looking at nested applications, And for the rest of the cases, you often get information pushed by the bidirectional typing mechanism. So this is a sweet spot, as I was saying. So our goal actually has always been to have a predictable inference, for which I mean a simple mental model that the developer can have of when things will succeed and also when things break, where the annotation should be placed. We also want obvious programs to be typable without annotations. And of course, what obvious are is subjective. In the paper, we have a big list of examples which we think should be typable without annotations. And many of the examples I've shown here are also typable without annotations. So we really want to push for getting as much impredicativity information as we can so that developers don't have to annotate all the time. The other goal we had is to be a conservative extension of existing features. So we want this thing to be compatible with type classes, type families, everything which is already into GHC, and also to be localized in specification and implementation. Because as I was saying, we want to implement this in GHC without massive changes. So let me talk a bit more about the fact that Quick Look is very localized. And as I said, this only affects instantiation. The rest of the type checking has no changes. So we've integrated this into GHC, which has type classes, type families, data type promotion, levity polymorphism, you name it. And we were able to implement this, and there is a merge request for doing so, and we only had to add 450 lines out of roughly 90,000 lines, which make up the type checker in GHC. So I think we succeeded in making this thing really localized. Of course, I encourage you to read the paper. There is more there. You have the full formalization, and actually we think it's the first time that bidirectional type inference and constraint had been written down in a paper. This is what was inside GHC, but there was nothing written about how you integrate all of this together. And on top of that, we built Quick Look impredicativity. Of course, we talk about meta-theoretical properties. Also, we talk about how we integrate Quick Look with visible type application, and the reason is that when Quick Look fails, the easiest way to override, the easiest way to tell the compiler what this instantiation should be is to use visible type application. So we think it's really important that these two things play together well. We also talk a bit about how qualified type and CRDTs integrate with Quick Look, and also lots of related work, because as I shown at the beginning, a lot of people have been struggling with this problem and trying to solve it for a long time. In summary, Quick Look impredicativity is a simple approach to impredicative inference, which tries to be predictable, but yet type as many obvious programs as possible without annotation, and it's also a conservative extension to what it's already there and very localized in specification and implementation. That's about all. I'd love to hear you any new ideas, any questions in the ICFP channel for this, and thanks for watching.
Thank you, Alejandro. If you are watching this talk live, please don't forget about the Q&A session that may be available in your time band. We will now pause here to sync up with the talk schedule. Our next talk presents a general mechanism in type system design inspired by modal logic. This work is called A Unified View of Modalities in Type Systems, and it is a paper by Andreas Abel and Jean-Philippe Bernardi, both from Gothenburg. Jean-Philippe Bernardi will be giving the talk.
Hello and welcome to A Unified View of Modalities in Type Systems. My name is Jean-Philippe Bernardi, and this is joint work with Andreas Abel. Modalities are qualifiers that modify types or propositions. For example, in the sentence, it may rain today, the rain today proposition is qualified with the possibility modality. Another possible example is the qualification of propositions by the agent who believe it, as in, John thinks that it rains today. In programming languages, it can be useful to qualify a type by an amount, representing how much is available. For example, 5.543 millimeters of rain. Another useful kind of qualifier is whether information is public or secret. In this work, our goal is to describe a system which unifies all such instances of modalities. We also want the system to have a useful meta-theory, which all instances can inherit. Our work is set in the framework of System F, also known as the polymorphic lambda calculus. I am going to assume familiarity with it. Also, I assume you know that they are isomorphic. If you watch this video offline, feel free to pause and read the slides at your own pace. Or you can consult the paper and come back later here. As suggested by the examples that I've shown above, we add a new type form a P boxed A, which I will just read out PA in the future. This means A qualified by modality P. To support model types, the key idea is to annotate every type variable, or every variable, with a modality in addition to its type. Again, to support model types, the key idea is to annotate every variable with a modality in addition to its type. Formally, what we do is to change the judgment so that it includes this little gamma here. It is a map from variable names to modalities. An important thing to note is that the resulting type A in the judgment has a unit modality. This unit modality will be interpreted differently depending on the application, but I can already say that it acts as a default modality. To produce A with another modality, say PA here, we need to multiply the modality context by P. That is, we multiply every modality in the context by P. In the same vein, if we want the product of A and B, then we need the sum of their respective modality contexts. To see how this plays out, let us first look at a fragment of plain system F without modalities. Then we can see how modality annotations get added. Let's look first at the variable rule. What it says is that A is used exactly once, and so A is annotated with the unit modality in the context. Also, that the rest of the context is not used at all, and so it is annotated with the zero modality. For consistency, we also annotate the domain of the hour type with the modality. You can see how this plays out in the ABS and EP rules, abstraction applications. In particular, in the application rule, to be able to feed QA to the function, we need Q times delta. In passing, we note quickly that the application does nothing useful with the modality context. Let's now look at the introduction and elimination rules for qualified types. The introduction rule works as we said before, namely, we multiply the context by P. The elimination rule is a bit more involved. Note first that we assume that little gamma produced PA. Now, we want to use this A to produce C in a continuation. We could think that we'd have PA in the context of the continuation, but instead, we are allowed to multiply by an additional arbitrary Q modality. This is because to produce one C, unit C, we may need another modality within exactly P for A. And thus, this version gives more flexibility to the programmer. On top of this, we also have an order on modalities, and it is generated by a semi-lattice, a mid-semi-lattice. This order drives a weakening rule, as shown here. We can also see the converse, and this is a conversion rule from P to Q if P is less than Q. The exact structure of modalities is as shown here. pause the video, or you can check out the paper. But the interesting bit is the last line, namely that addition distributes over meet. This property also implies that addition is monotonous. We can instantiate the structure to various special cases and obtain several useful systems in this way. First, we can do linear types. 0 and 1 acts as you'd expect. We just need to add the modality omega to support unrestricted usage. That's the bound modality in linear logic. The rest of the structure is as you'd expect, and omega is acting as a catch-all value. A useful generalization of linear types is as a system which tracks the exact number of times that a variable is used. However, one must allow for sets of possible usages to implement the meet at set union. The rest of the structure falls out from this choice. An interesting property of all such model systems is that a 0 annotated parameter is guaranteed not to be used. This is captured by the irrelevance theorem, which is stated as shown here and proven in the paper. The lattice, which, as you recall, corresponds to the order of modalities, can be used for various purposes. It can be used for security purposes, with more secret levels towards the top. It can be used to represent the necessity modality, with more necessary propositions towards the bottom. It can represent levels of beliefs. More credulous agents are at the top. It can represent computational relevance, with more relevant types toward the bottom. Remember that convertibility is from bottom to top, and so at the meet of P and Q, all data which is available for either P or Q is also available there. We can now take a moment to ponder what happens when one does not care about quantities, and so modalities are only used to represent levels in a lattice, such as shown previously. In this case, the meet becomes the addition and the join becomes multiplication. Additionally, 0 is also the top of the lattice. A consequence is that to produce 0A, or really top A, the modality context can be ignored, and so we can use all variables, even those that are available with modality 0 in delta. A last application where precise quantities are tracked is sensitivity analysis, which you can read about in the paper. Let's now turn to the meta theory. We consider first operational semantics, whose cornerstone is the substitution lemma. The proof follows the usual structure, but we have additionally to express how modalities are transformed by substitution. It turns out that the modality transformation applied by a substitution, here sigma, is a linear operator, here psi. The proof is straightforward, but it is interesting to note that the requirements necessary for modalities correspond exactly to the modality structure, which we have shown previously. We also have a modality-preserving abstract machine. This is a call-binding machine where every state is well-typed and well-qualified. The main point of showing this machine is to show that dynamic execution steps will never overconsume, underconsume, see private information, etc. So the modalities annotations can be realized at runtimes as such. Finally, we have a relational crypt case style semantics. We interpret types by relations, and these relations are indexed by worlds. The main novelty here is that we can interpret the PA type by a notion of division, or more precisely, a Galois connection. For quantitative systems, W is a multi-set of resources to consume. P is then interpreted as a natural number, and to interpret P at PA at a world W, we interpret A at a world W divided by P. For non-quantitative systems, W is a set of capabilities. Types are indistinguishable if the associated capability is not in W. We can take advantage of the fact that every modality can be represented by a set of capabilities. So, to interpret PA at W, we interpret A at the world, which is the difference of the sets W and P. Combining the two views is somewhat tedious, but it is shown in the paper. A perhaps controversial choice is that we have a constraint on which modalities can a value take to be scrutinized by a case expression. We demand that they must be convertible to the unit modality. This constraint is necessary for irrelevance. Otherwise, we will be able to see if we are on the left or on the right of the sum for every modality. And then everything becomes observable at every level, even 0. But the operational semantics do not, in fact, rely on this constraint. And so there are other choices. There is an extended discussion of this topic in the paper. Additionally, in the paper, we deal with the whole of system F, of course, with some end products. And we have quantification of modalities, which means that we have higher order model types. We also show more applications of free theorems, and we also give a wealth of nice details, so feel free to check it out. In conclusion, we declare victory because many useful systems can be captured by our framework, and it has indeed a rich meta theory. As future work, it could be useful to describe an application which exhibits a non-commutative multiplication. All those that I have shown so far don't. Another useful development would be to have a representation theorem for the modality structure. Thanks for watching.
Thank you, Jean-Philippe. At this point, please make sure to join a Q&A session if it is available in your time band. We will now pause to sync up with the rest of the talk schedule. Our next talk discusses pattern matching in the Glasgow Haskell compiler. It is based on work by Sebastian Groff, Simon Peyton-Jones, and Ryan Scott. The talk will be presented by Sebastian.
Hi, I'm Sebastian, and I'm here to talk to you about pattern match coverage checking. In case you're wondering how this problem hasn't been solved like 40 years ago, well, lower your guard and hold back on your judgment just for a few more minutes. Let's start with a quick recap about pattern match warnings. This incomplete definition of is just in Haskell here will crash when called with nothing, because it lacks a covering clause. Now, runtime crashes are annoying, especially for such an obvious oversight. So the compiler should, and indeed in the case of GHC it does, warn about it. I'll talk about how GHC figures out these missing cases. Apart from such missing equations like nothing here, compilers can also find redundant equations like the third one here. In fact, compilers have been able to produce these kinds of warnings for a long time, so you might think there's nothing new to find here. And I thought so too, before I picked up maintenance of GHC's pattern match checker as a side project about a year ago. As of recently, there are still 28 open tickets for the pattern match checker, most of them related to performance and incorrect handling of some subtle interaction of source syntax features. So how exactly can something that looks so simple give us so many headaches? Let's start with a little warm-up exercise. Is this function exhaustive? Well, that's a pretty suggestive question, and since this isn't a live talk, I won't be waiting for you. The answer is no, and these are the values that it failed to cover. There are only 4 pattern matches, but 16 different combinations of arguments to consider. Clearly, a scalable automated checker needs to know when and how to bail out of this exponential behavior. Now, Haskell is lazy, but not total. That also reflects in its pattern matching semantics. Take this function here as an example. It might be tempting to think that the second equation is redundant, but in fact it isn't. Deleting equation 2 would alter the semantics of the function from crashing to returning 3 in this call here, so not redundant. But on the other hand, we can never return to, which definitely smells like a bug worth reporting to the user. We say that the equation has an inaccessible right-hand side. Of course, when we call a clause redundant, that always implies its right-hand side is inaccessible. Lazy but not total also means that we have bottom inhabiting every data type. That includes the data type void, which doesn't have any data constructors, so bottom is its only inhabitant. These examples here introduce bindings of type void by resorting to divergence and runtime errors. F here matches on them in a lazy wildcard match, and it's just a regular exhaustive function definition. Now that we have void, we can combine it with strict fields. Here is a strict maybe data type, as you can tell by the strictness annotation on sJust's field here. Whenever sJust is constructed, its field needs to be evaluated first. The function f here matches on smaybe of void. Question: is the second clause of f redundant or not? We can answer this systematically by enumerating the inhabitants of smaybe void and see which equations of f match them. The only 2 inhabitants are bottom and snothing. sJust of bottom is not an inhabitant because of the strict field. The first equation of f diverges on bottom and matches on nothing. So yes, redundant. There is no value possibly reaching the second equation. Guards are another very basic pattern language feature of Haskell. Does sign have any redundant clauses? In general, it's hard to tell without knowing the definition of less than, eq, and so on. Also, we'd quickly become undecidable if we just reason about every function we know the definition of. So apparently guards are quite rich semantically speaking. Here you can see how it's even possible to do pattern matching with pattern guards. And get here even mixes both structural pattern matching and pattern guards. This definition is exhaustive and the compiler should not flag it as non-exhaustive. I hope it has become clearer that there are a lot of surface language features that the pattern match checker has to cope with efficiently. Also, many of these features interact with each other. I won't have time to talk about the ones in parentheses, like long distance information, so please do ask questions afterwards and read the paper if you're interested. The status quo in GHC was based on a 2015 ICFP paper that handles most of the language features in the previous list, including CRDTs and type-level information in particular. But having been battle tested over the last couple of years, the implementation revealed shortcomings in being too buggy and slow. Also, it was pretty complicated. In trying to improve on what we had, we iterated a couple of times and came out with a new approach we called Lower Your Guards. As the name suggests, we abandon all structural pattern matching, like in F here, and desugar function definitions into guard trees. Then we do coverage checking on these guard trees, which is split in two simple functions A and U. A returns an annotated tree, decorated with refinement types that capture redundancy and inaccessibility information. If you want to know more about this part, I encourage you to read the paper. U computes the set of values that weren't covered by any clause as a refinement type theta. And then all we have to do is report the inhabitants of theta as uncovered patterns of the definition. Let's desugar this fancy example function. Green indicates source syntax. You can see that fancy makes use of constructor patterns and even two language extensions, a bang pattern that forces the matched thing, and a view pattern that applies the matched thing to G and matches the result against true. In yellow, you see fancy's desugaring to guard trees. Here is the syntax definition for reference. Let's focus on tree syntax first. There's one branch in the guard tree for each clause in the function definition, modeling fall-through semantics. There are also a bunch of guards on each branch, and each branch ends in an ordinal that identifies a particular clause in the original program. Looking at guards, we can see that nested pattern matching was completely decomposed into multiple flat pattern guards, like on just here. Pattern guards are considered lazy, and evaluation is forced by bang guards, such as on x1 here, which stands for the first argument. Pattern guards can only match on variables and only one level deep at a time. We give names to more complex expression like this function application with a let binding, which also allows us to desugar the view pattern here, for example. Desugaring also introduces a few administrative lets that fix up naming differences, like the one binding access to the temporary T2 here. We found similar desugarings for all the pattern match syntax of modern Haskell. Also note that this desugaring is for coverage checking only. There is no code generation involved. Alright, next up, characterizing the set of uncovered values that we can report uncovered patterns for. We compute the set by gradually refining the set of possible values as a fraction of them falls through from one clause to the next. How do we represent such a set with possibly infinitely many values? We picked refinement types for the job. Here are a few example refinement types in blue, as well as the sets they denote in orange. Cross is the unsatisfiable refinement predicate, so there are no inhabitants. Checkmark is the trivially satisfiable refinement predicate, which means we have all the inhabitants of bool. This is the type of unlifted booleans, and this one also rules out false. This last one here shows what's unusual about our refinement types. It has a pattern guard on mx that brings just field x into scope, which then scopes over the conjunct to the right of the pattern guard. For some reasonably simple end-to-end example, consider this source program. It will desugar to this guard tree, which in turn we can compute the uncovered set for. Note that the resulting refinement type has a disjunction in its predicate, because we can fall through from this clause here in two different ways. First, the match on just could have failed, and even if the match on just succeeded, the match on true could have failed. Question now, how do we do this in general? With a function like this, U computes the subset of theta whose values do not match the guard tree T. When we reach the right-hand side, every incoming value is covered, so we return the empty refinement type. Branches model fall-through semantics. Only values that fall through the first branch can fall through the second branch. A bang guard on X adds the constraint that X can be bottom to the incoming values of the subtree. Likewise for let bindings. A pattern guard matching against constructor K will fall through when X is not K. Also, everything not covered by the subtree is uncovered, so we adjoin the two refinement types. And that's all there is to coverage checking. The next step is to generate inhabitants of the refinement type falling out at the bottom. These are the uncovered clauses which we want to report to the user. If it's empty, then the pattern match was exhaustive. For our particular running example, the inhabitants are easy to find. Just true and just false, which are already in a suitable form to be presented to the user. Algorithmically, we could use liquid Haskell's embedding of refinement types or an SMT solver directly to generate inhabitants. But we didn't do that because reflecting GHC's type constraint solver into SMT logic is quite an undertaking. And we think that FFI calls and serialization of facts incur too much overhead. So we bit the bullet and just wrote our own ad hoc generator function. You can read more about its implementation and its completeness properties in the paper. Now, for an uncovered set coming from an obviously exhaustive definition, like H here, we find that we can produce any inhabitants. So, no values to represent, hence no warnings to emit. H is found to be exhaustive. In conclusion, we came up with what we find to be quite a nice solution to pattern match coverage checking. It took us many iterations to get there, but in the end it paid off. The end result is at the same time simpler to think about, simpler to implement, and executes much faster. The fact that we invented it for a lazy language shouldn't stop you from lowering your guards in strict or even mostly imperative languages. Just write your own desugaring function. And if you're in the process of writing a coverage checker and don't want to make the same mistakes, I can only encourage you to read the paper. Lots of more stories to be told about language extensions and efficiency concerns. Alright, that's it. Thank you for listening.
Thank you, Sebastian. If you are watching this talk live, be sure to join the Q&A session with the author if it is available in your time zone. We will now pause to sync up with the rest of the schedule. The last talk of this session is Signature Restriction for Polymorphic Algebraic Effects. This paper is by Taro Sakiyama, Takeshi Tsukada, and Atsushi Igarashi. The talk will be presented by Taro Sakiyama.
Hello, I'm Taro Sakiyama. This talk is about our ICFP paper, Signature Restriction for Polymorphic Algebraic Effect. In this work, we consider a new type-safe approach to combining two programming features, algebraic effect handlers and polymorphism. Algebraic effect handlers is an approach to user-defined effect, and they can also structure effectful programs in a modular way, thanks to the separation of interface and implementation of effect. Using algebraic effect handlers, we can define various effects, such as exception, backtracking, state, and interactive I/O. Another feature we consider in this work is polymorphism. In particular, we consider implicit polymorphism as a ret polymorphism. And by combining these two programming features, we can make not only expressions, but also effects polymorphic. Okay, so let's show one example of using algebraic effect handlers and polymorphism. And algebraic effect handlers provide three constructs to implement the effect. The first construct is effect declarations, which is used in the first line of the running example. Here, the operation choose is declared with this polymorphic type. So this type means that the choose operation takes two arguments and returns either of them. Here, polymorphism allows the type of choose to abstract over the type of argument. The second construct is operation calls, which is used in these expressions. Here, the arguments to choose operation calls are first and second functions for pairs. So both of these functions can be of this polymorphic type. So the result of this operation calls is also assigned the same polymorphic type. The third construct is for define effect, and which is achieved by the use of effect handlers. So effect handlers are a key component in defining effects, but in this talk, I omit the details of them. So, so the problem we consider in this talk is that the naively combining algebraic effect handlers and implicit polymorphism. So this is a problem because the naive combination of these programming features makes statically typed language unsafe. This is because algebraic effect handlers have the ability to manipulate delimited continuations, but the naive combinations of the use of continuations and implicit polymorphism is known to be unsafe. So this is a problem we attacked in this work. But this is a classic problem. So there are many approaches to solving this one. So the existing approaches can be classified into two categories. The first category is consider the restricting operation calls in polymorphic expressions. For the running examples, the approaches in this category restrict these expressions because this is an operation call in a polymorphic expression. For example, value restriction, weak polymorphism, closure typing belong to this category. An advantage of using these approaches is that they can address any effect, including ML style reference and control operators. However, disadvantage of these approaches is that they impose a restriction on any effect code. Because, for example, even if the operation code doesn't need restriction. For example, we found in the previous work, exception and backtracking don't need a restriction, but the approaches in this category don't distinguish effect that need a restriction and effect that don't need a restriction. So they impose a restriction for all effect. As a complementary approach in the previous work, we provided a new approach to restricting effect handlers instead of operation calls. So in the running example, this approach restricts this part effect handlers. A good point of this approach is that it allows operation calls of safe effect anywhere, and it rejects unsafe effect safely. But the problem of this approach is that it is not clear how to mix the safe and unsafe effects in a single program. So this could be a problem. This could be a problem in the general purpose programming because we may want to use safe and unsafe effects in a single program. And to solve this problem, we propose a new approach which restricts the types of effect operations. So in these running examples, this new approach restricts effect declarations. And we can determine whether any usable effects are safe only by examining this type. Okay, so let me summarize our work. We propose a signature restriction, which can ensure safety of effect with polymorphism. And the signature restriction accepts only effect that can be safely used anywhere, even in polymorphic expressions, without any other restriction. The signature restriction examines the typed signatures of effect. So it is very simple criterion. But it is still permissive in the sense that it can accept many useful effects. And it is also scalable. It means that the signature restriction can easily support basic programming construct, including the products, sums, and the list. And to show the correctness of this signature restriction, we provided a simple type system for algebraic effect handlers and polymorphism. We show soundness of the simple type system by assuming all effects satisfy the signature restriction. So this demonstrates the correctness of the signature restriction. But the problem with this simple type system is that we cannot use both effects that satisfy and don't satisfy the signature restriction. So to solve these situations, we propose an effect system where both safe effects and unsafe effects can be used. And more precisely, in this effect system, effect that satisfies the signature restriction can be used anywhere without restriction, but if effects don't satisfy the signature restriction, then they can be used only in monomorphic expressions. We also provide an artifact that implements a tiny, small, ML-like functional programming language where all effects are supposed to satisfy the signature restriction. And this implementation does not cover the effect system part. Okay, so this is a quick summary of our work. And next, I will present a brief overview of signature restriction. As I said, signature restriction is an approach to determine the safety of effect with a signature of effect. So let's suppose we consider these operations with this polymorphic type. Here, the signature restriction determines the safety of effect only by examining the properties of alpha in argument type tab 1 and return type tab 2. More formally, we can say operation satisfies the signature restriction if and only if alpha occurs only negatively or strictly positively in argument type tab 1, and alpha occurs only positively in return type tab 2. Here, let me remember what does mean by strictly positively. So in this simple function type, the occurrences of alpha 1 and alpha 3 are positive, but only the occurrence of alpha 3 is strictly positive. This is because the occurrence of alpha 3 is reached by going through only the positive part of function type, but the occurrence of alpha 1 is reached by going through a negative part of function type constructor. So this is a difference of the properties of alpha 1 and alpha 3. And by using these definitions, we check the 3 operation calls satisfy the signature restriction. The first example is choose. So we can easily find this type of choose satisfies the signature restriction, because for the argument type, the bound type variables occurs only strictly positively. And for return type, it also occurs only positively. So this choose operation satisfies the signature restriction. And we can apply similar discussion to the Fay operation. For the satisfy operations, this function, this argument type may seem complicated, but the priority checking is very easy. We can easily find that this type, in this type, the bound type variable alpha occurs only strictly positively. So satisfy operation also follows the signature restriction. And as a result, all of these 3 operations satisfy the signature restriction. Okay, so this is our work, but our work does not cover all useful features in functional programming language. For example, this work does not cover type inference and general algebraic data types. So the support for these features is left as future work. And we also considered studying CPS transformation for this restriction method and applying the signature restriction to other user-defined effect mechanisms, such as monas. It should be interesting, we consider. Okay, let me summarize this talk. The problem we attack in this work is that the naive combinations of algebraic effect handlers and polymorphism may be problematic. To solve these problems, we propose a signature restriction, which is a new approach to determining safety of effect in a polymorphic setting. And the signature restriction rests only on the properties of bound type variables. So it is very simple. It's just examining the signature of an effect. And it is still permissive and scalable. And we provide a simple type system and prove its soundness by assuming all effects satisfy the signature restriction, and which demonstrates the correctness of signature restriction. And we also provide an effect system where both effects that satisfy and don't satisfy the signature restriction can be used. That's it. Thank you for listening.
Thank you, Taro. If you are watching this stream live, don't forget about the Q&A session that may be available in your time band so that you can discuss this work with the authors. This is the last paper in session 4. Thank you for attending. you.